So now we're getting onto kind of the applications of why we're going to use vectors. So the first one is in projectile motion, and the second is with inclined planes. So when we're working with projectile motion, we need to apply vector analysis to determine the horizontal and vertical components, and then from there solve problems. So we're going to get onto projectile motion now. So when we work with 2D motion, we need to resolve our vectors, including velocity, acceleration, and displacement, and apply our 1D kinematic formulas to each dimension individually. So, situations where acceleration is constant can be described by these formulas here. So remember, projectile motion is a case where our acceleration is constant because the only acceleration that we're considering is acceleration due to gravity, which is always 9.8 meters per second towards the ground. So because our acceleration is constant, we can apply these formulas. Now, of course, remember there is the other factor of air resistance. However, in year 12, we don't consider air resistance. So even though air resistance is like an acceleration factor because it would be slowing the projectile down, we can kind of assume that it's negligible because it's going to be so small. And then we can also describe the average velocity and acceleration with these formulas. I'll just quickly give you guys an overview of what projectile motion looks like and some important things to kind of pop in your notes. Remember that the maximum height of a projectile occurs when the velocity in the y direction is equal to 0. Remember that the horizontal velocity is going to be constant because there's no acceleration acting in the horizontal direction. There's only acceleration acting downwards or vertically. So there's going to be acceleration vertically but not horizontally. Remember the reason why the maximum height occurs at Vy equals 0 is because the projectile is decelerating, or it's getting slower and slower when it's moving upwards because the force of gravity is acting against it. So it is going to have the largest vertical component at the beginning here, and then it's going to slow down, and at a certain point it's going to stop going up and start going down, and that is when it's going to turn around, and its velocity in the y direction is now going to be negative because it's falling downwards. So it's positive, 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 but it's getting smaller and smaller and smaller. Now it's negative, negative, negative. So that's why that occurs. Okay, now we're going to get onto an overview of circular motion. So remember, we are describing uniform circular motion. We're going to be going over the concepts of average speed and period. And then we're going to solve problems using the formulas in our formula sheet and also go over the terms centripetal acceleration and centripetal force. So One tip that I have for you guys, just as you're kind of maybe making notes in preparation for your external, because I know you guys, you don't have any internal exams, but you need to be preparing for your externals. Something that I'd recommend, especially for physics and also other sciences, although I didn't do them, I imagine that this would also help. Um, for kind of syllabus dot points like this, where we need to define centripetal acceleration and centripetal force, it's really useful to make notes or flashcards of the QCEE definitions of these two terms. And the reason for that is in your external, you're going to have 20 multiple choice questions, and a decent amount of those multiple choice questions are going to be on like definitions. They're just going to say like, oh, like what's the definition of this term? And they're going to give you like 4 different options, and you need to pick one. The correct one is always going to be the QCEE definition, the official one. So if you memorize those throughout the year, those easy 20 marks on the multiple choice are going to be no-brainers for you. So the reason that it's important to memorize these is because they'll often try to trick you up and kind of change a few words around. So if you don't know the QCEE definition, you'll spend too long kind of going through the options and thinking about them. It's way more efficient to just know the terms before you go into the exam, so you can spend that time going through the other, like the short response and long response. If you're looking for where to find the QCEE definitions, all you need to do is go onto the syllabus, the big PDF document, and then Control F, like search the document for the term. So I'd Control F centripetal acceleration, and then go down until the end of the document where the glossary is, and then find that definition and just copy paste it into your notes. Absolutely saved me. Brilliant tip. The other thing, which I will get into when we get into more of the electromagnetism topic, is how you can actually remember like the explain syllabus dot points. We'll get into that later. Okay, so getting onto our centripetal acceleration, our circular motion, don't know what I'm saying. So when a force acts to constantly change the motion of an object, then the object will follow a circular path. So the net force in circular motion is always directed inwards, and this is kind of, before we get into the other elements of circular motion, I'll just explain one thing to you guys, which is kind of a common misunderstanding with circular motion, and that is that, like, a misunderstanding of like why the force is acting inwards and the acceleration is acting inwards. Like, how are you accelerating inwards towards the center of motion if you're kind of moving in a different direction? So one way to think about this is, of course, that if you're moving at a certain velocity, you're being kind of, there's like a force holding you to the center of motion. So you want to move off, but there's a force holding you there. So think about perhaps a ball on a string that you're kind of whirling around in a circle. The ball itself at every point wants to move away in the exact same direction that it is traveling in at that moment, right? It's one of Newton's laws. The object will always want to travel in the way that it's going at that moment unless acted on by another force. So in the ball's case, the string in the center is holding it and forcing it to go around in this direction. So it's always actually accelerating inwards because it's always kind of being pulled back towards the center of motion. Another thing to think about with circular motion is, of course, the I think the misunderstanding about why, when you're experiencing circular motion, you feel like you're being pulled away from the center of motion. This is something that I remember when my teacher told me in year 12. I absolutely did not believe him. He said, no, 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 the force acts towards the center of motion. And I said, I do not believe you. But it makes a lot of intuitive sense if you think about it really hard. And mind you, it took me a couple of months to finally understand this. So imagine that you are driving, right? You're just driving along a road, a straight little road, and you brake. You brake really hard. I don't know, maybe you see something, there's a cute little bird walking across the road, you brake really hard, and you feel yourself being like thrown forward into the front, into the steering wheel, right? Which makes sense. So even though the car itself is slowing down, your body kind of acts in the opposite direction because it wants to continue in the motion that it had before. Previously, it was going like 100 k's an hour, but now it's slowed to nothing, and your body wants to keep moving at 100 k's an hour, but it's been acted on this force which has now stopped it from moving like that. So it's going to continue and like move forward. It's inertia, right? Your body has mass, so it takes energy to move it. So thinking about this in the context of circular motion, if you are driving around a roundabout, or I don't know, you're doing a donut or something, but driving around a roundabout is probably safer. You're driving around a roundabout, you feel like, I mean, if you're going fast enough, you feel like you're being pulled away from the center of motion. But that's because the force is pulling you inwards, but your body is resisting that change because it has inertia. I hope that finally makes sense for you guys. If you still don't understand the concept, please put a question in the live chat and I'll answer it. But now that the conceptual stuff is out of the way, let's get into more of the formula specific stuff. So, as you can see here, the real force underlies a theoretical centripetal force that causes centripetal acceleration and a change in velocity. Remember, the velocity is changing. However, the only reason the velocity is changing is because the direction at which the ball is moving, or the object is moving, is constantly changing, but its speed is not changing. So the velocity changes in direction, but not magnitude. The ball is moving at a constant speed, but it's changing direction. The average speed of the object is going to be given by distance over time. The distance is, of course, going to be the circumference of the kind of this circle that we're considering, which is going to be 2 pi r, circumference is 2 pi r, divided by time. The acceleration is going to be given by velocity squared divided by the radius, which is going to be equal to 4 times pi squared times the radius divided by the period. And then the force, the net force, is going to be equal to mass times acceleration, or 4 pi squared r times m divided by the period squared. So all of these formulas are in your formula book. It's kind of a case of practicing, applying them, and just kind of having a basic understanding of the concept.